This is part two of the chapter two lecture notes, and I think we had finished this pretty much, except I wanted to add um, there is another isotope of carbon that is not shown, and it's carbon 14, and you could probably guess how many neutrons carbon 14 contains. But carbon 14 would be, the symbol would be written like that. And then in order to get the number of neutrons, you would subtract 6 from 14, and that would give you 8 neutrons. So you can see that there are 3 isotopes, and you don't get the atomic mass by just averaging 12, 13, and 14. Um, you actually have to account for the fact that there's more carbon 12 in nature than there is carbon 13 and carbon 14. So you have to average the percentages of each isotope. And luckily, we don't have to worry about that in biology. But I just want you to understand the atomic mass is an average of all of the isotopes of an element, whereas the mass number is just the atomic mass rounded. So if you'll just round it to the nearest whole number, that will give you the mass number of the atom so that you can calculate the number of neutrons. So let's look at another example of isotopes. There are 3 forms or 3 isotopes of hydrogen. Hydrogen 1 is the most common form, and it is called protium. And if we call it hydrogen 1, that means 1 is the mass number, okay? So for hydrogen 1, the mass number is 1. It tells you here that hydrogen 1 has 0 neutrons, and you can also see it from the diagram. There is 1 proton, and I'm just going to put a plus here so you know that's a proton. The proton has a positive charge. There is 1 proton in the nucleus, and that's where the mass number 1 comes from. And then there is 1 electron in the first energy level, and that is where the negative charge comes from. So remember, there's always got to be an equal number of protons and electrons, or else the atom will have a charge, and we'll call it an ion instead of an atom. So for hydrogen 1 or protium, there's 1 proton and 1 electron. For deuterium or hydrogen 2, mass number is 2. There is 1 proton and 1 electron, and then there is 1 neutron. So the mass, I'm just going to put it as an N for neutron because we know it's neutral. It has a 0 charge. So the overall mass number is 2 because there are 2 particles in the nucleus, a proton and a neutron. And so that is the second isotope of hydrogen. The third isotope of hydrogen is called tritium. So you have your proton in the nucleus, you have your electron in the first energy level, and then you have 2 neutrons. So that gives you a mass number of 3. So that's another example of isotopes. This video is on slide number, I have to look it up for you, sorry. I can't see it from my view. Okay, so it's slide number 11. If you would like to watch it, I don't like to show a recording of a video that you could just click on and watch, later. But this is a video that explains isotopes and atomic mass. So you can go back to slide 11 later if you need to. So here is a slide showing an example of isotopes being used in research. The isotopes that are used in this case are radioisotopes. Radioisotopes are isotopes of an element that emit radiation in the form of neutrons, protons, and electrons. So when these radioisotopes emit radiation, we say that they decay. Over time, they decay. These isotopes decay. And so, therefore, you can use a mathematical formula comparing the percentages of different isotopes of an element in a fossil. And you can use those percentages to calculate the relative date or estimate the date of that fossil. You can use carbon-14, the isotope of carbon-12, carbon-14, which is the one that has 6 protons and 8 neutrons. And carbon-14 is a radioisotope that can be used in dating fossils that are less than 50,000 years old. So this pygmy mammoth, these bones that these researchers are very painstakingly trying to recover, are the fossilized bones of a pygmy mammoth. And so the age of that pygmy mammoth can be determined using carbon dating. But for older fossils, we have to use different radioisotopes like uranium, potassium, or rubidium. So that's just one use of radioisotopes. We also use radioisotopes to do scans like thyroid scans and PET scans, that kind of thing. And this is just the periodic table. Every element has its own little box, and each box has information in it. So let's just look at one random, I don't know, I'm just spotting Mn stands for manganese. I'll write that out for you. It's probably the only time in biology class that I will ever mention manganese. Sounds a little bit like magnesium, but magnesium is Mg. So manganese has, I know it's small, so I'll try to write it a little bit bigger for you. Symbol is capital N, lowercase n, and it's got an atomic number of 25. And then if you round the atomic mass, you can get the mass number. The atomic mass is 54.9 something, so that would round to 55. So we could use this information to calculate the number of protons. So there are 25 protons. That means 25 positive charges. And therefore, there would be 25 electrons. So the negative charges balance out the positive charges. And then if you subtract 55, take away 25, you get 30. So manganese has 30 neutrons, which are neutral. And this information is available for all the elements in the periodic table. Some other things that are available to you by looking at the periodic table are the group number tells you, we're going to talk more about this, but just so that you understand it, the group number will tell you the number of valence electrons in all the atoms in that group. So group number 1, for example, has 1 valence electron in its outer. A valence electron is the number of electrons in the outermost energy level outside the nucleus. So in group 1, there's 1 valence electron. Group 2 has 2 valence electrons. Group 13 has 3 valence electrons. 14 has 4. 15 has 5. 16 has 6. 17 has 7. And 18 has 8 valence electrons. And except for the case of helium, all of the atoms in group 18 have 8 valence electrons except for helium. Helium only has 2 electrons, so it has 2 valence electrons. But all the rest of them have 8 valence electrons, which means that they are stable. That means 8 valence electrons means that that energy level is filled up. It's completely filled with all the electrons it can hold, and that means that that atom is stable. So all the other groups are chemically reactive. In other words, they will form chemical bonds with each other, with other atoms. But the elements in group 18 are the noble gases, which are chemically stable, and they do not tend to form chemical bonds. And you can also learn information from the periods or the rows. Period 1, for example, tells you that the atoms in that period have one energy level. And then period 2, they have 2 energy levels. And period 3, they have 3 energy levels, and so on, all the way to 7 energy levels. And there may be more than that, but I know there's at least 7 that an atom can have. Atoms typically have a neutral charge. If they don't, if they have a charge, a positive or a negative charge, then we don't call them atoms anymore. We call them ions. So the number of protons or positive charges will equal the number of electrons or negative charges. And so therefore, the number of electrons can be found from the atomic number, since the atomic number is the number of protons, and we know the number of protons equals the number of electrons. So when we try to figure out where the electrons belong, as far as which energy levels that they are located in, this hydrogen model shows 3 energy levels, but hydrogen only has 1 electron because its atomic number is 1. And so therefore, it doesn't have a second or a third energy level. It doesn't need one. It has the first energy level, which is 1n, has the 1 electron in it. But the first energy level can actually hold 2 electrons, and then the second, third, fourth, fifth, sixth, and seventh energy levels can hold 8 electrons. They are complete or filled with 8. The first energy level is filled with 2. So you can see that for hydrogen, hydrogen is in group 1. Hydrogen has 1 valence electron in its first energy level. So it is not complete, it is not stable, and it can form chemical bonds. It's going to form chemical bonds in order to make sure that it does have 2 electrons in its first energy level, so that its valence shell is filled. Now group 18, helium already has 2 electrons in its first energy level, so we say that its valence shell is filled with 2 electrons. Then if we look on to period 2, you can see lithium has an atomic number of 3. So that means it's got 2 electrons in its first energy level and 1 electron in its second energy level. And the second energy level is the valence shell. So it's got 1 electron in its valence shell. And neon has 8. It's got 2 in its first energy level, and then it's got 2, 4, 6, 8 in its second energy level. So lithium is unstable because its valence shell, its second energy level, is not filled. It would take 7 more to fill that valence shell. Neon, however, is stable because its valence shell is filled with 8 electrons. You can look at these other examples and see the same type of thing. But basically the group will tell you how many valence electrons that the atom has. Group 1 has 1 valence electron. Group 14 has 4 valence electrons. Group 17 has 7 valence electrons. Group 18 has 8, except for, again, the exception is hydrogen and helium in period 1. Well, it's not really, hydrogen's really not an exception, but helium is an exception because helium is stable with only 2 electrons, and that is because the first energy level is filled with 2. The second, third, fourth, fifth, sixth, and seventh energy levels are filled with 8 electrons. And that rule is called the octet rule. When the valence shell or the outer energy level is filled with 8 electrons, then we say that that atom is stable. So what atoms do is they try to react with other atoms in such a way that their valence shells become filled.